Alright, so today we're going to look at discontinuity. So, just like the word sounds, okay, we have continuous functions that have continuity, right, because they flow from left to right with no breaks. And then we have discontinuity, meaning that there are breaks in the graph. So, graphs that we have dealt with so far generally are continuous, meaning I can get from one side of the graph to the other without ever picking up my pencil. So this would be continuous. Now, discontinuities come in many different forms, but anytime you have a graph and you have to pick up your pencil to finish from left to right, that is a discontinuity. Okay? So there are many different types of discontinuities. All we're going to do today is focus on those different types and how we find them. So let's look at the first type. First type of discontinuity is an infinite discontinuity, and we've dealt with these a lot in previous units. Okay? Infinite discontinuities are things that go off into infinity. So those would be my asymptotes. Okay? And primarily today, we're only going to focus on vertical asymptotes. Okay? The next unit, or the next topic we're going to do is all the different types of asymptotes. We have vertical, horizontal, and slant asymptotes. But we'll get into all of that next time. So we find vertical asymptotes whenever my denominator equals 0. So anytime you have a rational function, rational meaning fraction, right? I'm going to set my denominator equal to 0, and that's how I find that infinite discontinuity, that vertical asymptote. Now, given a graph, it's a little bit easier. We don't have to do any math. We can just look and see, okay, I have an infinite discontinuity, and that infinite discontinuity happens at the vertical line, x equals 3. Okay, now, when we're describing discontinuity, you have to say what type it is and where it happens. Okay, now you can't just say infinite at 3. Okay, I don't know what that means. You have to say x equals 3. Okay, that's the vertical line, x equals 3. Now, number 2, we're not given the graph, but we're given the function. Okay, so I'm going to set my denominator equal to 0. So x plus 3 equals 0. So that means at negative 3, I have an infinite discontinuity at x equals negative 3. So that would be my answer to that. Okay. Now, sometimes we have quadratics or cubics in the problem. A lot of times, those can be factored. So, if I look at my denominator here, numerator I can't change. But the denominator is a perfect square minus a perfect square. So I'm going to do my difference of squares here. So that would be x and 2. So I would have x plus 2 and x minus 2. Setting my denominator equal to 0, that means that I would have an infinite discontinuity at negative 2 and 2. So we would say infinite at x equals negative 2 and x equals 2. Okay, so that's finding our vertical asymptotes, my infinite discontinuity. Next, we have removable discontinuities. Now, removable discontinuities are whenever I have a hole in the graph, and that's literally represented by a hole in the graph. Now, holes are different than what we've seen previously and what we're going to talk about next, which is a jump, where you have the solid dot below or above the closed dot, the open dot, right? That's a little bit different. See, a hole in the graph is it's continuous everywhere else, and then literally there's just an open dot, and then the line continues after the open dot. Okay, so that's a removable discontinuity. Now, we find removable discontinuities by things that cancel out of the problem. So when I factor the numerator and the denominator, if something cancels out of that, that's where the removable discontinuity happens. So let's look at the image first. Okay, here is my hole. All right, so I would say I have a removable discontinuity at, and then the x value where that happens is at x equals 2. Alright, number 5, we got to factor first. So I need factors of negative 12 that add up to 4. That would be 6 and negative 2. So this would be x minus 2, x plus 6, all over x minus 2. So after I factor it, I see that I have x minus 2 on top and bottom. That cancels. And again, whatever cancels is what's going to make the hole on the graph. So I would say I have a removable discontinuity at, and it's not going to say at x equals negative 2, right? I would say set that equal to 0 to figure out what the x equals. So at x minus 2 equals 0, which would be x equals 2. Now, once I do that canceling, I see that this no longer has a denominator. So there's not an infinite discontinuity with it. But let's look at number 6 here. So we'll start by factoring top and bottom. So factors of 6 that add up to 5. Positive and positive, so that would have to be x plus 3, x plus 2. Factors of negative 15 that add up to negative 2. So we would have x minus 5, x plus 3. So cancel the x plus 3's. Okay, so that would leave me with x plus 2 on top, x minus 5 on the bottom. So this is going to have a removable at x equals negative 3, right? And this still has a denominator. So setting that denominator equal to 0, I would have an infinite discontinuity at x equals 5. Okay, so that has 2 types of discontinuities. All right, so that's infinite and infinite and removable. Now we're going to look at jumps. Okay, so jumps are literally what it sounds like. When you're moving from left to right, you literally have to jump from one part of the graph to the other. Okay, so this is generally when I have a piecewise function. Okay, and what's really happening here is I have a different y value from the left and right hand side of a particular x value in the problem. So when I look here, I see that here's my jump. Okay, and that happens at x equals 2. So I would say I would have a jump discontinuity at x equals negative 2. Now, when I'm given a piecewise function, we're going to take the value that's in the domain over here. So in this case, it's 2. I'm going to plug 2 in to both equations. If the number I get, or the answer I get, is different on top and bottom, that means I have a jump discontinuity. If it's the same, then it's going to be continuous. So I would have 2 plus 4, which would give me 6. So that's the top, right? On the bottom, so here's the bottom, we have 2 times 2 minus 3, so 4 minus 3, which would give me 1. Because 6 does not equal 1, that means that this is discontinuous. Okay, so we do have a discontinuity, so we would say we have a jump at that x value, x equals 2. Alright, so now let's look at 9. I wonder what's going to happen here. Okay, so we're going to plug in negative 1 to the top and bottom. So on top, have negative 1 squared minus 2. So that would be 1 minus 2, which gives me negative 1. On the bottom, 3 times negative 1 plus 2. So that would be negative 3 plus 2, which is negative 1. Since negative 1 equals negative 1, it's not different, so there is no jump. So we would say that this is continuous. Okay, so you have to check. Now, graphically, what this looks like. For number 8, that means I would have something like this. Okay. and it's going to jump. So it would look something like that. Okay. Now for number 9, the top is a quadratic. Okay. And then I would have the open dot there. And then the bottom is a line, which would be a closed dot, like that. Okay. Since the closed dot falls in the open dot, that makes it continuous. I don't have to pick up my pencil and jump from the left side to the right side. All right. Now, let's look at some examples of kind of putting all this stuff together. So first we'll look at, given a graph, identify what type of discontinuity it is and where it happens. So, looking at number 10, I see 2 different types of discontinuities. I have a hole here, and then a jump here. So we would say we have a removable, right, the hole, and that's at x equals -2. And we have a jump at x equals 1. Now, number 11, I also see 2 discontinuities, but it's 2 of the same. Okay, I see 2 infinite discontinuities. So we have infinite, right, 2 vertical asymptotes. So the first vertical asymptote happens at x equals -3 and at x equals 3. Now, looking at 12, I don't see any discontinuities, right? So when that happens, we just say this is continuous. All right, now let's look at when we're given equations. Okay. So again, step 1 is always to factor. Okay, if you can ever factor when you have a rational function, we want to do so. So factoring the top. Now, this time I have something with the x squared. So I'm going to have to do a little bit more work to figure out those 2 factors. So, AC method. A times C. So there's A, there's C. That gives me -12. Has to add up to 1. So that would be 4 and -3. So 2x squared plus 4x minus 3x minus 6. Do your grouping. So take a 2x out, and we would have x plus 2. Take out a -3. So my 2 factors there, I would have 2x minus 3 and x plus 2. So that's the top. Now the bottom factor is a little bit easier. I need factors of -10 that add up to -3. That's going to be -5 and 2. So we would have x plus 2, x minus 5. See if anything cancels. I see that I have x plus 2 on top and bottom, so those cancel. So I'm left with 2x minus 3 on top, x minus 5 on bottom. So this is going to have 2 discontinuities. First, the canceling gives me a removable. Right? That's the whole. And that's going to be when x equals -2. Now I'm also going to have an infinite, right? I have a denominator here. So set that denominator equal to 0. I would have an infinite vertical asymptote, right? At x equals 5. Alright, so there's 13. Now 14. I got to do some factoring again. So 6 times -1 would be -6. Has to add up to -1. So that's going to give me -3 and 2. So 6x squared minus 3x plus 2x minus 1. Do your grouping. Take out a 3x. And we can only take out a 1 out of that. So 2x minus 1. So on top, I would have 3x plus 1 and 2x minus 1. Now I've got to do the same thing on bottom. A times C, so 2 times -3 is -6. It's got to add up to -1. So again, I get negative 3 and 2. So 2x squared minus 3x plus 2x minus 3. Do your grouping. So we have x, 2x minus 3. Again, I can only take out a 1, positive. 2x minus 3. So my factors on bottom, I would have x plus 1 and 2x minus 3. Now, nothing cancels, right? So we're not going to have a removable discontinuity, but I do have 2 factors in my denominator. So I'm going to set each one of those equal to 0, and that's going to give me my infinite discontinuities. So we have 2 infinite discontinuities at, so x plus 1 equal to 0, that would be at x equals negative 1. And setting 2x minus 3 equal to 0, I would add the 3 and divide by 2. So that would be at x equals 3 over 2. Okay. All right, 15 piecewise. So this may or may not have a jump. The only way I can check is by taking that negative 1 and plugging it into top and bottom, seeing what I get. If it's different, we have a jump. If it's the same, it's continuous. So let's plug into the top first. Negative 1 squared minus 4. So that would be 1 minus 4, which gives me negative 3. On bottom, 2 times negative 1 minus 1. So negative 2 minus 1 gives me negative 3. So negative 3 equals negative 3, which means that this is continuous. All right, last one, number 16. This is a quadratic, right? X squared minus 4x plus 3. There's no denominator, so nothing will factor out and cancel, so there's no removable discontinuities. Again, there's no denominator, so there's no infinite discontinuity. It's not a piecewise function, so there's no jumps. And there's no vertical asymptotes here. So just by the function type it is, it's a quadratic, we know that this has to be continuous. All right, so that is discontinuities.